Hey everybody, today we're going to solve the complete binary tree inserter problem on LeetCode. The problem description says a complete binary tree is a binary tree in which every level except possibly the last is completely filled, and all nodes are as far left as possible. We want a data structure called CBT inserter. It's initialized with a complete binary tree and supports the operations of a constructor which takes a complete binary tree's root, a insert which inserts a node with value v, maintaining the complete binary tree property, and returns the parent's value, and then get root, which will just return the root of the tree. Alright, so for this problem, what I ended up doing was modeling this similarly to how you model a heap as an array, okay, because using an array makes looking up the parent value very easy, inserting new values is easy, and it requires that the binary tree remain complete. So the way it'll look is it will be the tree nodes will be held in a array, okay? The root will be at index 0, and the calculations are pretty simple. So the left child of some index I is 2 times the index plus 1, and then the right child is 2 times the index plus 2. Now, calculating the child isn't very difficult or important for this problem. What is important is being able to calculate the index of the parent. So, when you are inserting at some index, that parent, the index's parent, is going to be in the array at index of the child minus 1 divided by 2. Okay, so doing that, we can quickly look up the parent, and once we can do that, we can just attach it to the parent, and that's all we have to do for the insert. So here's what it looks like. The data structure maintains an array list and tree. Again, like I said, we're maintaining this tree represented as an array, and the constructor does a lot of the work. So we make a new array for our tree, and then use level order traversal to initialize that array. And let's see what that looks like. So down here, I wrote this level order traversal, and all that does is it traverses the tree in level order, and the nodes that are visited in level order are the order in which they will be inserted into the array. Okay? So all we have to do is add the root, and then if you've never seen level order traversal, it's basically a modified version of breadth first traversal, breadth first search. So once we run through this level order traversal, we've added all nodes into the array in the order they need to be inserted. So the get root function is very simple. It just gets the index at 0. The root is always at 0. And then after we've run our level order traversal and we've initialized the array, then insert becomes pretty easy. And insert's the only other part that's doing any work. So to insert into this tree, we obviously need the parent, right? And because of the structure of this array that we have, the parent is going to be in the array at index that we're inserting at, which is the new node that's being inserted, minus 1 by 2. So this is how we find the parent in the array. And then once we have that, it's real simple. We just make a new node out of the value that they're asking. If the parent's left is null, remember, for a complete tree, all nodes are as far to the left as possible. So if the parent's left is equal to null, then we just set the left to be the new node, else the right is the new node. And then we just add that into the array, which I just call tree. And then we return the parent's value, because that's what they want out of the problem. So let's see what that looks like. Alright, so not too difficult of a problem. The key observation really is the idea of by storing the tree in an array, you can enforce the properties of a complete binary tree.